Welcome to today's webinar. Today's webinar is given by Mark McGann. He's the Senior Principal Scientific Software Developer at OpenEye. And the title of his talk is going to be Billion Scale Virtual Screening in Orion. If during the webinar you have any questions, please put them in the Q&A box. So we'll read them and get to them at the end of the webinar. And without any further ado, I'll hand it over to Mark.
Thank you, Gunther, and thanks everybody for coming. Yeah, today I'm going to talk to you about doing some really large-scale virtual screening in Orion, as Gunther mentioned. I'm going to start off with just an overview of the entire presentation, what we're going to run through, and then I'm going to run through 3 different programs that we have to do this ultra-large virtual screening, one of which is a ligand-based screening program, and 2 of which are structure-based programs. So first, what is Orion? Orion is a computer-aided drug design platform that sits currently on top of Amazon Web Services. So it's a cloud-based service that you interact with through a web browser. And it has all the power of the cloud. So you can do lots of things in Orion. You can analyze data, you can visualize your molecules, you can collaborate with others. But most of what I'm going to talk about today is the calculational power. And we use this to do some really large-scale virtual screening into the scale of billions. And virtual screening libraries are getting larger and larger. When Orion was initially deployed in 2019, the largest vendor libraries were around 1 billion. And I mean, at that time was about 1.4 billion molecules. And they have continued to grow. We have many of these kinds of vendor libraries pre-prepared in Orion for any users of Orion. It makes it very easy to screen these libraries with the programs that I'm going to show with you. You can also prepare your own in-house libraries. With the reaction enumeration, you can easily get to libraries this big, and it's not that uncommon for large pharmaceutical companies to have similar virtual libraries of this size. And you can prepare those in Orion to screen with these programs as well. The flows I'm going to talk about are FastROCS Plus, and that is a feature-rich ligand-based screening program that's in Orion. I'm also going to talk about Gigadock and Gigadock Warp, which are structure-based programs. There is an additional ligand-based program called Batch FastROCS that's just a sort of maximally efficient but less featureful FastROCS Plus, or version of FastROCS, I should say. But it's not really used very often because FastROCS is already incredibly cheap and the cost efficiency usually doesn't matter. Usually we're talking the difference between costing $20 and $5 or something like that. So I'll start off with FastROCS Plus. And the question I'll start with is, what is FastROCS? And FastROCS is a 3D similarity of ligands, and it can do these calculations at scale. To do this similarity, though, we represent molecules as shapes where the atom centers have Gaussians that sort of represent the density of the atoms on them. And we also represent color points, which would be things like ring centers or hydrogen bond acceptor and donor positions, or atoms, as Gaussians as well. And then what we do is, using this representation of 2 molecules, we overlay the screening molecules onto some query molecule of interest that you're trying to find something similar to, using some clever Gaussian math. And the really nice thing about this is that this overlay only cares about the general shape and chemistry, and it doesn't actually directly care at all about the connectivity. So you often find in 3D similarity calculations, as opposed to 2D calculations, you can often find very different chemotypes rather than just all molecules of the same series. And that's really with the power of doing 3D similarity rather than 2D similarity. What FastROCS does in Orion is you can give it billions of molecules, either these pre-prepared vendor databases that I talked about before, or your own database of molecules that you have prepared within Orion. And you give it 1 or more query ligands for your target. And this FastROCS is then run on a GPU. FastROCS is the GPU version of ROCS on the Amazon Web Services. And it does this calculation, and you get an output hit list that by default is 10K, but you can make up to 100,000 molecules if you want. And you also get this novelty hit list, and I'll explain what that is in a little bit. But this is really the primary ligand-based flow for doing screening, ligand-based screening in Orion. And the cost to screen 10 billion molecules, which is currently our largest vendor collection, Enamine, is approximately $200. So this is really cost efficient for a very sophisticated 3D overlay. In addition to the FastROCS hit list, You also get a ROCS hit list where we've taken the top scoring molecules from FastROCS and we've re-overlaid them with ROCS, which is the CPU version. And the reason that we actually enable this is you can actually give it a different query for ROCS. And what people use is they'll often use a sophisticated shape query. So both ROCS and FastROCS support more than just using as a query a simple ligand molecule. You can actually annotate molecules and identify specific color points that are important and things like that. But there are some limitations that ROCS can only do some basic modifications this way, whereas ROCS, the CPU version, can do the full suite of support for doing customization of your queries. So if you have that, what you would generally do is for the input ligand query, you would actually give it this basic shape query. FastROCS would find the molecules that score the best. And then the flow allows you to give a full shape query that's very sophisticated to ROCS, and it will rescore on. And you get a hit list from that. You also get a novelty hit list. Again, I'll explain those in a little bit. Finally, there is an option in FastROCS Plus to also do some structure-based screening. If you are working with a project where you also have a receptor, we call it often a design unit, but it's the structure of a protein that you know you want to hit, you can optionally give this to FastROCS Plus. If you do that, it will also take the top molecules from FastROCS and it will dock them into that receptor conformation or the design unit that you've given it, and it will produce a docking hit list. And it will also automatically produce a consensus list of the molecules that both ROCS and docking like. So now I'm going to go over a little bit of how the novelty and the consensus list work. And they both work using this concept called a Pareto frontier. So this is a kind of ranking method of sort of getting basically data that's interesting in two or more different dimensions. I've shown an example here for 2 dimensions where we have 2 different scores, and higher is better in this example case. And the Pareto frontier is the set of molecules for which there is no other molecule that exceeds it in both scores. And what that winds up being is effectively this red surface that you see here. And these tend to be interesting molecules in this case. And what we do with the novelty hit list is we prioritize molecules that have high 3D similarity using those Gaussians that I described earlier that ROCS and FastROCS use, but have low 2D similarity. So we're trying to prioritize molecules that are different chemotypes, but still have the same shape and chemistry. And we use this Pareto frontier method here. So we favor molecules that have low 2D similarity in one axis, and we favor molecules in the other axis, the other dimension, that have high 3D similarity. So this is really good for scaffold hopping. And you tend to get a hit list that's about in 100 or 200 molecules in this technique. So it's a more manageable number of molecules to go through, and they tend to be rather different. So they do range from molecules that have basically super high 3D similarity. There'll be a few that are like that, and relatively high 2D similarity, which we're not going for, and vice versa, the really low 2D similarity and high 3D and low 3D similarity. But you also get this really interesting range in between that are relatively high scoring in 3D and relatively low scoring in 2D, which again promotes scaffold hopping. The consensus for docking, if you've given FastROCS Plus a design unit or receptor conformation, is very similar. We use the same Pareto frontier approach, and here we favor things with high 3D similarity and good docking scores. And again, the consensus list winds up being in the size of about 100. So it's a nice, manageable amount. And this is, I think, both of these are really nice features for FastROCS Plus. You get the novelty hit lists automatically. They just come out naturally from FastROCS Plus when you run them. You get the docking consensus hit list if you have given FastROCS Plus a design unit or receptor conformation as well, but that's purely optional. And people get good results using FastROCS Plus. This is an example of just an overview of one of our customers, Beacon. They were trying to identify some novel chemical space for a GPCR target. They had 2 molecules from literature that they couldn't take forward in their own chemotypes, basically, because they had basically various issues with them. So they were looking for new kinds of chemical space, different chemotypes, and they ran FastROCS Plus. And what they did is they looked at the hit list by hand. I think they said they went through about 1,000 molecules. They selected 30 to order, and then they assayed those. They got 11 hits, the best being 2.2 nanomolar. And the most important thing here is they found novel chemical series that they wanted to take forward in their project. So these just weren't active molecules that looked like the molecules they had before. These were new kinds of active molecules. So now I'm going to move on and talk to you a little bit about Gigadock. So Gigadock is a docking program for billions of molecules. And I just want to cover the algorithm first that's used for the docking. This is the same algorithm that OpenEye uses for its docking programs, Fred and Hybrid in the OE docking suite. And it's the same method that's embedded in Gigadock. There's no change to the algorithm itself. And the way that algorithm works is you get conformers of a docked molecule as input. So we pre-enumerate the molecule's conformations. This is done in the preparation process. So generally, you don't have to do that. And then we enumerate all the conformers of each molecule we're docking in the site by exhaustively sampling them in rotational and translational space to a resolution of 1 angstrom. So we generally wind up with a very large number of molecules like this that fit into the site and don't clash, usually about 10 to 100,000 molecules. Sorry, not molecules, poses. We then score all of these poses. And we do that either if there's 2 different modes you can use. There's a Fred mode, which is a pure structure-based design mode, where you score the molecule with ChemGauss3, which is a structure-based scoring function that measures how well the pose interacts with the protein. Does it fit well? Does it make good interactions? Or if you're using hybrid at this stage, what it actually measures is it looks for molecules that best overlay a ligand that was that the protein was either crystallized with or was in the cryo-EM structure that you generated. So it's trying to find molecules, it's guiding the poses that it's scoring based on those that best match the existing ligand. In either case, the top 100 scoring molecules are selected, and they are then rescored with ChemGauss4, which is a more sophisticated scoring function. And that's a structure-based scoring function that, again, looks for complementarity to the active site in terms of shape and matching chemistry. And then we output the top scoring pose. The Gigadock flow uses this algorithm, either Fred or hybrid, and it takes a set of billions of molecules. You can give it less, but usually people will be screening billions of molecules in Orion, and a receptor or multiple receptor conformations, or design units as we often call them. And of the molecules who give it the billions, the Gigadock flow docks every molecule. It doesn't skip or do any approximation, does a full docking on every single molecule. You get an output hit list that's 10K in size. You also get a collection, which is a specialized container Orion for large amounts of data, that contains every pose of every molecule that was docked and its score. This flow has been in Orion since Orion's initial release in March 2019. It was really the original killer app of Orion, and it remains in Orion. You also have the option with the Gigadock flow to give it known active molecules. And the purpose of this is, say you have a project with some molecules that you know to be active, and you want to know whether or not your docking is going to be successful against your particular target. Most virtual screening tools tend to perform differently on different targets. Sometimes they do really well on one target, sometimes they do relatively poorly on another target. This is just a feature of basically all virtual screening programs. But what the Gigadock flow will let you do if you have known active molecules, and say you're preparing to screen 1 billion or 10 billion molecules, you can actually select a sample of the molecules you're planning to screen against, say 1 million molecules, and you can give that set to the Gigadock flow along with your known active molecules. And if you do this, Gigadock understands what you're trying to do, and it produces a histogram that shows how your known active molecules screen against that subset of molecules you docked with as well, the sort of background set. And what you're looking for is that your active molecules will tend to score better than the background set of molecules, because most of those are going to be inactive in general. So you're looking for the active molecules to be scoring better. And this is just a way of checking ahead of time, am I likely to get good results when I dock to this particular target? And it sort of is a way of addressing the issue in that there's a high amount of variance in virtual screening performance, often from target to target. You get all the docked molecule actives in addition to normal output, as well as an AUC measure and the histogram when you do this. So this is just a great way of basically determining if your performance is likely to be good, or if you have multiple receptors, conformations of the same target, you could actually try this with each one and use that to determine which receptor is likely to give you the best result, which receptor conformation. And Gigadock does work. This is another example from Beacon Discovery, where they screened entering real 1.4 billion molecules. They did this validation, like I told you to begin with, to sort of know that their target was likely, they were getting good results from it. They synthesized 56 compounds. They found 22 hits. The best was 223 nanomolar. Again, this was an interesting novel chemical series that they wanted to bring forward in their project. We've also done our own test against HSP90. We screened, again, enemy real 1.4 billion molecules at the time. We validated this also with known actives. We ordered 120 compounds, got 37 hits. The highest activity was 4 micromolar. This is actually that hit. It's the #1 top scoring molecule of the $1.4 billion screen. Sorry, not $1.4 billion, 1.4 billion molecule screen. And what I want you to get out of this by looking at these images is these molecules are really different. The top scoring molecule here that's 4 micromolar reaches into an entirely different part of the pocket. The original molecule doesn't. And this is really the reason that often people want to do structure-based design, aside from having an available structure and maybe not known active ligands, versus doing ligand-based design. And that is, you tend to get much more novel molecules when you do structure-based design. And this is just an example of it. Now, the cost of a Gigadock run is significantly more than FastROCS Plus, and it scales linear with the number of molecules, and it also has a tendency to increase with the size of the receptor site. So larger receptor sites tend to take longer and are therefore more costly to dock to. And that's because there's more space to explore, more scoring to be done per molecule. What I've shown in the graph to the right here is an estimate of the cost per billion in screening. And this tends to be around $10,000 to $15,000 per billion. And at the time when Orion was initially released in 2019, a billion was a typical size of a library. Now, $10,000 to $15,000 is a fair amount of money, but within the context of an important drug discovery process, this is actually an amount of money that people are often willing to spend for an important project. But these days, enemy real is now about 10 billion in size. And that means to do a full Gigadock, you're really talking about $100,000 or more, typically for most receptor sites that you're going to do. And that is often beyond the budget of most drug discovery projects for a virtual screen. And this is why I'm going to start talking about Gigadock Warp, and it was really the driving force for the development of Gigadock Warp. So what is the concept? The concept of Gigadock Warp is to be a drop-in replacement for the Gigadock flow that uses artificial intelligence to improve the efficiency of the calculation. This was initially released in 2021, a couple years ago, but we made a substantial improvement this June, so of June of last year. And we also are, I think by the time you see this webinar, we will have released the March release, which does further improvement. But the way Gigadock Warp works is you give it billions of molecules and one or more conformations of your receptor, exactly the same input that you would give the Gigadock flow. And then underneath the hood, it randomly selects a certain percentage of those molecules to do normal docking on. And it takes those results and uses them as a training set for the local regression model that we're going to build, that it builds automatically under the hood. And it's a regression model for the score that's based on the properties of the molecule. But you don't have to, with this model, you don't actually have to dock the molecule to estimate the score. So we then predict the score of all the remaining molecules using this local model. And then we dock a percentage of the molecules that the model predicts will be high scoring. And we dock them at the end, this certain percentage, using the normal docking process. And you get a hit list of up to 100,000. You don't get the collection of every docked molecule because Gigadock Warp is explicitly avoiding docking every single molecule. And we think that this is an ideal use case for AI within our field. And that's because AI is an empirical model. And that means that it can interpolate, but it can't really extrapolate. Large learning models like ChatGPT, things like that, they have very impressive results. And one of the reasons that they're so impressive is that their training data is vast. They've scraped essentially the entire internet for training data. And that's why these models seem so powerful. But in our field, say you're trying to predict experiments, we have a very limited amount of training data compared to something like ChatGPT or any of these large language models. And the data can be limited for experimental data, and it can be of poor quality. So it's very hard to train an AI model to predict an experiment in our field because our data just isn't very vast and it's not that great. But what AI can do in our field is we can try to predict a computation that's relatively expensive to calculate directly using the normal computation. But if we can train a model, we can predict the result of that computation much more efficiently often than doing the actual full computation itself. And this is exactly what Gigadock Warp does. And most importantly, because we already have the capability of docking billions of molecules, we don't actually have to dock quite that many for the training set, but we can dock many molecules, often millions of molecules, and make that the training set. So we have a lot of training data to use, or to be basically to use to train the model. So our purpose here is to reduce the compute time. And the overall goal of Gigadock Warp, therefore, is to be a drop-in replacement and to produce as closely as possible the exact same hit list that you would get from Gigadock, but at a fraction of the computational cost. So we are trying to improve the efficiency of the calculation. We're not actually trying to improve the quality of the results from Gigadock, which are good, but the purpose of AI here is for efficiency, not improved quality of calculation. And because of that, I just want to cover just briefly what the cost centers are of this flow. For the Gigadock flow, that's actually relatively straightforward. It's almost all the docking. So if you do the analysis, you wind up with about somewhere above 95% of the cost is just in the docking. It's efficient in some sense, but it's costly overall. For Gigadock Warp, there is a cost to doing docking because we dock some of the molecules at the beginning and some more molecules that the model likes at the end. And whatever total percentage we get, that percentage of the full Gigadock cost is incurred by the Gigadock Warp flow. There's also a cost associated with featurizing the molecule. Some featurizations are more expensive than others. You need to do this featurization, though, in order to prepare the molecules for the model. And there's also a cost of building the model score. We do this on a relatively small number of machines, but they're expensive GPU machines. And they can have some modest amount of cost that contributes to the flow. And finally, there's some I/O overhead. The data set, the size of the input data for the current Enamine 10 billion collection is around 40 terabytes. And that data gets enlarged during the process of this flow because we have to compute the featurization and attach that. And that data then moves around a lot. So there's actually almost probably, I would estimate, about half a petabyte of data that moves through this flow in various points. And there's some I/O overhead associated with that. So that can be costly as well. So now I want to talk to you about the AI algorithm that we use and the kinds of featurization that we tested. In this section, I'm just going to go through what these featurizations and hyperparameters that we looked at are. And in the next section, I'm actually going to show you results on how, if we vary these things, how we do. So the first hyperparameter is just what fraction of molecules do we dock? What fraction do we dock initially? When we're generating our training set, so we select a random X%, and then what fraction of molecules after we built the model and determine what molecules in the remaining set that the model likes, what fraction of those do we dock at the end? And we have found that if you hold these two parameters the sum of these two parameters constant, the initial random docking and the final docking, if you hold that constant, you're almost always better to have used a smaller number of molecules to build a training set and more molecules at the end that you're docking that the model likes. And this is just something we see over and over and over again. The flow cost will in general increase linearly, or this portion of the flow cost, the docking cost, will increase linearly with this total sum of X plus Y here, the total fraction that we do. Presumably performance will also increase as well, but there's a balance here because we're trying to basically be cost beneficial. We could just set these to 100% and we would get the exact same answers, but it's like taking a shower with a raincoat on because we're trying to save cost here. The second hyperparameter is the number of active learning stages. So what we can do and what we've tested is instead of building a training set using a given fraction of molecules at the beginning and then just predicting the scores and docking those molecules at the end, we can add more molecules to the training set. So we can dock a certain percentage of molecules as training data, build the model, and then we can ask the model, what molecules do you like? And the molecules that it likes, we can add back into the training data and build another model with that combined set of training data. And the goal here is to have the model better distinguish molecules that have high scores. And when I show you the results of these, the thing to remember is we keep the percentage of molecules that are used as training data constant as we increase the number of active learning stages. Here I've shown 2 stages, but we can obviously do more. But if we're comparing, say, 1 active learning stage, which is really no active learning, where we dock 1% of the molecules as training data, and then we compare it to 2 active learning stages, then the initial set of training data is 0.5%. We build the model. Then we select the top 0.5% of the molecules that the model thinks score well and add those also to the training data and rebuild the model. So our total training set size is still 1%. So we keep that constant when we do this comparison because we think that's a fair comparison to how active learning does. Another hyperparameter is the type of score regression model that we use. So we've tried 2 here. We have a basic linear model, and we also have a neural net model. And in this work, our neural net model is a 2-layer model with 100 nodes per layer and a rectified linear unit activation function. And we also examine the effect of trying to train multiple neural net models and see if one of them is better than the other, or if we get a substantial improvement by training multiples and trying to pick out the best. And I'm just going to cover the 3 types of featurization that we examined. So again, featurization is just how do we take a molecular structure and then convert it into a set of numbers that's just going to be a list that we can then feed into our machine learning model. And I'll show you some results later on where we're combining different types of featurizations, and all we do is append the feature vectors when we do this. So the first kind of featurization I just call simple 2D property, and this is really what I consider to be a null model. It's the most basic kind of featurization I could think of, and it includes things like molecular weight, atom counts, bond counts, total number of rings, things like this. All super trivial to calculate properties of a molecule that are based on the graph of the molecule. And in addition to calculating these properties, we also compute the squared terms and the cross terms between those. And this gives us a feature vector that's about 377 long, or excuse me, exactly 377 long. But again, this is the most basic null model that we can think of for featurization. The second kind of featurization we use, we just call fingerprint featurization, where we take some fingerprint that's a series of bits that are either on or off, and all we do is we take that series of bits and we represent them in the feature vector as 0s or 1s. And that just makes up a feature vector. In this results that I'm going to show you, I'll always be using a 4K tree fingerprint. We've examined different kinds of fingerprints that are 4K, and they all perform about the same. There's really not much difference. I'll just tell you that now. There is an effect on smaller numbers, smaller number of bits. So if you use a feature vector, say like max key is 166, that tends not to do so well. But the results I'm going to show you here, will you be using a 4K tree fingerprint. And again, that means the feature vector is just 4K of 0s or 1s that represent the individual bits that are on or off in that fingerprint. The last kind of featurization I think is the most interesting, and it's what we call FastROCS featurization. So what we do here is we look at the training set of molecules and we find the molecules that score the best from the training set, and we have their docked poses. So these are the highest scoring molecules in the training set. And we use these high scoring docked poses as queries for FastROCS. So then for every single molecule that we're trying to featurize, which is the entire remaining set of molecules of the initial billions that you've given it, we do a FastROCS calculation. We overlay that molecule onto each one of these top scoring training poses. And we compute the shape and color similarity of those overlaid molecules onto the docked query poses. So for every query pose, we get 2 numbers in our feature vector. One is the shape, and the second is the color, tanimoto of the overlay. So in the results I'm going to show you, we actually select the top 100 top scoring molecules from FastROCS, and we wind up with a feature vector that's 200 long because we have both the shape and the color Tanimoto in the feature vector. So now I'm going to go through what happens when we adjust these hyperparameters and try different kinds of featurization. But first I'm going to explain the testing and how we actually did these tests. So for these tests, we docked 1.4 billion molecules with Gigadock, and we use this as the ground truth. So in the systems we're using as test systems, we first run Gigadock with 1.4 billion molecules so we can identify the exact 10K hit list we want to be getting from Gigadock Warp. Again, the goal here is to reproduce the Gigadock hit list with Gigadock Warp. And we found that it's important to actually operate at this scale. We tried doing some optimizations, or doing the kind of optimization I'm going to show you at smaller scale, on the scale of 1 to 10 million. And what we found is the results that we got weren't the same. So optimization at small scale, like in millions, compared to optimization for billions, doesn't seem to have the same optimum, basically, or the ideal procedure for doing that isn't the same. So I would be cautious if you were trying to do a similar approach to this and you were trying to adjust your hyperparameters and optimize them using a small set of results, like on a million, and expect that you'll get the same results on billions. It's just our experience. We did 5 Gigadock runs to establish the ground truth against 3 different targets. 3 of those runs we used with Fred, the standard structure-based approach to docking, and 2 of those we used hybrid, where we pay attention to the bound ligand structure in the receptor, and then we use that to guide the poses. And finally, I just want to mention, when I'm showing results, if I don't specifically mention these things, the percent of trained molecules will be 1% by default. Again, we vary that, but by default, it's going to be 1%. So that's 14 million molecules, because that's 1% of 1.4 billion. By default, we're using a linear model. Again, I have examples for when we use the neural net, but if I don't mention it, we're using a linear model. And finally, we use 1 stage of active learning by default. Again, I have results for multiple stages, but if I'm not talking about it, it's a 1-stage model. And last, I just want to talk about the metric that we use to evaluate the score model that we're building in Gigadock Warp. So what we do is we initially take all the molecules that Gigadock docked and we order them by score. We then identify the top 10,000 molecules in the true Gigadock hit list. We then build the model that the regression model that Gigadock Warp uses, and we reorder the molecules by the predicted score of this model. But we've still marked the molecules that should be in the top 10K hit list. And then using this, we construct a receiver operator curve, where on the x-axis is the non-Gigadock hit list molecules, and on the y-axis is the hit list molecules. So we want this curve to be as high and to the left as possible, because that indicates that the Gigadock Warp hit list model's prediction is doing a really good job of predicting the actual score. And we compute the AUC, the area under the curve, which will approach 1 as the model becomes perfect as well. And I use that in a lot of the graphs that I show you. I'll just show you the AUC, although I do have receiver operator characteristic curves as well, ROC curves. And the ROC curves are really nice for a particular reason for us, and that is the x-axis is the number of non-hit list molecules. And what that effectively becomes is it tells us if we select a given fraction of molecules to dock at the end, so molecules that the model predicts to score really well, if we select a given percentage, it tells us what fraction of the true Gigadock hit list molecules will be in the output Gigadock Warp hit list. So we don't have to vary that hyperparameter in multiple runs. We can just look at that curve and we can determine that. And the area in the curve will also relate to this as well. So here's the first real set of results. So here I'm comparing different kinds of featurization. Remember, I had the simple no model 2D featurization. I also have the 4K tree fingerprint featurization, and I have the FastROCS featurization. And on this graph, one of the more interesting things is that the mineral corticoid receptor, both in Fred and hybrid mode, which are the first two groups to the left on this graph, do relatively poorly. I actually find this interesting. I actually don't know at the moment exactly why that is. I would have expected the opposite because the mineral corticoid receptor happened to be the smallest receptor site. And my intuition told me that the model would tend to work best with that. And yet it doesn't. So there's something subtle going on here that's making this a more challenging target for Gigadock Warp relative to the other targets. I think it's also interesting to look at the same graph if you switch the axes, which is what I've done here. So now on the x-axis is the type of featurization, and the colors in the bars represent which target. And what you see here is the two sort of 2D type methods, so both the 2D simple 2D properties and the tree featurization. They do relatively poorly on the mineral corticoid receptor, and they do relatively much better on the other receptors. Whereas the FastROCS, which is a 3D kind of featurization, it works more consistently across all of the different targets, the mineral corticoid and the other receptors here. So there's a good mean performance, particularly for the tree featurization. It's higher than any of the others, the mean performance. But the FastROCS 3D featurization is more consistent. It's not doing really well on one and really poorly on the other. It tends to be doing the same on most of them. So the natural thing that you would ask here is, it's like, well, can we just combine these featurizations? And that's exactly what we did. And that's what you see in these results. So here I've shown in the first three bars here going from the left are just the mean result that you saw on the previous slide using just one of the featurizations. The error bars here are the maximum and minimum performance, or AUC, on any individual target of the 5 Gigadocks we ran, or the 5 Gigadock Warp 1 runs we ran. The remaining 4 are just when you combine these kinds of featurizations. And what you find out of this is relatively unsurprising. If you combine and have a larger, more descriptive featurization, you start to do better. Particularly when you're using the FastROCS and the tree fingerprints, you do really well. Throwing in the simple 2D properties helps a little bit, but it's a really minimal effect. But these are also super cheap to include. So in our results and in the release version, we actually use the FastROCS tree and 2D fingerprints when we do this. So everything I just showed you was using a linear model. And the question is, what happens if we switch over to using the neural net model I talked to you about? And the answer is that the neural net model becomes better in every single test system. It has really good results. Now, this wasn't the case when we initially tested this in the spring. So the release that came out last summer, in the summer of 2023, used a linear model, because when we tried a neural net model, we actually got worse results. But I knew at the time that something funny was going on. One of two things had to be happening here, because the neural net model could be as good as the linear model. And that's because there's a configuration of the neural net's coefficients that makes it replicate the linear model. So it was certainly possible for the neural net model to be optimized in a way that produced, at least matched, the linear model. And there's really two reasons that the neural net model, when we initially tried it, wasn't working very well. The first is either the molecule was overtrained, or the model was overtrained, or the model wasn't well optimized. And when I thought about this in the in the early fall, when I was thinking about this more, I realized that the model really was very unlikely to be overtrained. And that's because we have 14 million training molecules for the model in this case. We have 1.4 billion input molecules, 1% of that is 14 million. And the number of coefficients total in the neural net between all the nodes is only about 500,000. So we had about 25 times the amount of training data than we did number of coefficients in the node, and that in the neural net. And that means that it's really unlikely that we were overtraining the neural net model itself. So that left optimization, and we ran a test and we optimized the neural net for a very long time. It took about 2 weeks. And what we found was that indeed we started to get better and better results. That was too much to put in. 2 weeks is too long to optimize a model for a production software program. But since the summer release, we put in the technical work to improve the speed of optimization. I'll skip all the details. Happy to answer questions later about this. But we can now optimize the neural net model about 12 hours, and these are the results that you're showing here. So this is a really big win for a neural net model. It wasn't trivial to get, but it's working really well in this case. And I think our thought that this was an ideal use case from AI is justified by these results. And that, again, the real reason for that is we have tons of training data here. This is what the receiver operator characteristic curves look like if you compare a linear and the neural net model, both with the same set of featurizations. The neural net model is better here. It's a little hard to see on this scale, though. This is the complete receiver operator characteristic curve that you're looking at here. So in the next slide, I am actually just zooming into this section, which is really the section that's of most relevance to us. And here it's a little clearer that the neural net model is performing better than the linear model. And in fact, remember I told you that on the x-axis here, this is if you choose the x-axis to be the percentage of the molecules that you dock at the end, the percentage of molecules the model likes that you then go do real docking on. The y-axis then tells you what percentage of the Gigadock hit list you're going to recover with Gigadock Warp. And for the linear model, that was the summer release, we used 8%. In the upcoming, or I think at this point, currently released March 2024 model, we dropped that to 4% with this neural net, and we still get an overall improvement in performance. So we're saving cost even more, and we're getting still better performance. We did investigate using multiple neural net models. So we built up to 5 different models, and we tried to choose the best, that seemed to fit the data the best. And what we found here is that all the models that we built all seem to perform about exactly the same. I think these models are actually really well optimized now. And my intuition from what or not just my intuition, but what I've seen in the data here is they all appear to be optimizing to the same optima, hopefully a global optima, but they seem to be optimized really well here. So in the release version, we actually only build a single neural net model because we haven't found any improvement by building multiples. And again, I expect this is because the neural net model was fed training data that far exceeded its number of parameters. So we didn't really have to worry about overtraining. And I suspect that's why this seems to be working so well. We also tried varying the size of the training data. So we tried halving it from 1% to 0.5%, and we tried doubling it to 2%. And there's really no systematic benefit here. In fact, in one system, increasing the size of the training data actually made it slightly worse. But I think this is well within the noise of just some random noise and variation here. We actually, in the release version, we default to using 1% training data. This is actually adjustable in a parameter. And the reason for that is this is not actually a particularly significant cost center in this flow. And I was worried that if people happen to be using Gigadock Warp to dock small numbers, relatively small numbers of molecules, say 100 million or so, then the percent of training data might need to be a little bit larger. So because this wasn't a particularly large cost center, we just left this at 1% as the default. Again, this is an adjustable parameter in the flow. And finally, this is what happened when we tried increasing the number of active learning stages, but controlling that the total percentage of training molecules was constant. So we tried 1, which is our default, which is really no active learning, 2 active learning stages, and 4. And for the mineral corticoid receptor, there is an increase in performance that you see, and there does seem to be a trend in improvement. In the other cases, there's no real clear trend of improving performance. We didn't actually enable multiple active learning stages in the release, though. And the reason for that is while there is some evidence here that there's improved performance by doing active learning, it also significantly increases the I/O overhead of the model. Going from 1 to 2 active learning stages effectively doubles the amount of data that gets moved around in the flow, and similarly going from 2 to 4 doubles it again. And the I/O cost is actually not trivial. It's not a majority with 1 active learning stage, but with 4, it becomes a very significant fraction of the cost of the flow. And remember here, our goal is to be cost efficient. And we just felt that while the active learning did give a benefit here, in some cases, it wasn't worth the additional cost that was really associated with a lot of I/O overhead when we did this. So that's why the release version only uses 1 active learning stage. So finally, I just want to show you some real-world cost performance here. And that's really summarized in this table right here. So this shows for the 5 systems that we ran Gigadock on, what the cost of the Gigadock flow was, so doing the complete docking on the 1.4 billion. I've also shown the Gigadock Warp cost. When we ran the exact same input through the Gigadock Warp flow, I can show what that costs. And I also show you what percentage of molecules were similar between the Gigadock and Gigadock Warp hit lists. So our goal is for 100% similarity and as low a cost as possible. I also shown this on a graph on the right where we want to see things in the upper right corner, upper left corner, which means that they had a very low cost and they had a very high similarity between the two hit lists here. And the bottom line here is we're getting about, on average, 90% of the molecules similar between the Gigadock and Gigadock Warp hit lists. Sometimes it's a little better, sometimes it's a little worse. And we're doing that at about 1/10 of the cost. So this is a huge win for Gigadock Warp. And given how good these results are now with the current release, I think that people should always be using the Gigadock Warp flow in place of the Gigadock flow if they're going to be docking billions of molecules. This is just a comparison to some of the historic versions. We've really had 3 major releases. So we had the initial release in December 2021, we had the June release last summer, and we had the current release that just came out in March. And this is a little bit of a zoomed in version of the same graph, so you can see the difference. But what you get out of this is that there's a general progression. We're going more and more into the upper left. So less cost and more molecules recovered that are similar to the Gigadock hit list. So we've definitely made some real improvements. I'm actually super pleased with this latest release. I think it's a really solid release, and I really don't have any hesitance recommending using Gigadock Warp in place of Gigadock when you're going to dock billions of molecules. It's 1/10 of the cost, and you get almost all the same molecules at the end. So in conclusion, Gigadock Warp is a cost-effective replacement to Gigadock, and the current release that we just released in March is a huge improvement over the previous releases. And I just went over a bunch of insights into the model itself. I'd be happy to answer any questions about that more, but that's the end of my talk. And at this point, I'll be happy to answer any questions. Thank you very much.
We're back live, Mark, here in the Q&A session. So thanks, everybody. Thank you for the talk, Mark. If there are any more questions from anybody, please put them in the Q&A section here, if you didn't put them in already. And we do have a few questions already. Let me see. First one here is, why not group the molecules by similarity and pick representative molecules to train the AI as opposed to a random selection?
So that's a good question. And that's actually something that's on our to-do list. So we think that, so selecting randomly is easy. So it was something that was relatively straightforward to do in this process. And we wanted to see that the models actually worked in general. There's also, there's a lot of ways you can select a representative set of molecules. So there's a bunch of ways to do that. And with really large numbers, some of them become quite complicated. The strategy we're probably going to take is most of these libraries that we're screening are actually enumerated reactions. So they're just reaction enumerations. And we're probably going to experiment in the future with trying to sample, basically make sure we get a good sampling of all the reagents or reactions that go on. In that way, that's sort of the strategy we're probably going to try first. There's a lot of different ways, though, you could do this. But in general, it's a good idea, and it's just something we haven't gotten to yet.
Okay. Another one I see here is docking seems the most costly part. So you do 10% real docking. Can we get away with less than 10%?
We probably can. So, I mean, I had here. Let me see if I can get to this slide here. Give me a second here. Pull it up. So I do. Oops, wrong one. Oh, here, actually, we can still get there. Where are the number models? Size of the training set. Yeah. So here, basically, I've shown what happens, if you have slightly less molecules that we're training with. And it does seem we can get away with a model with smaller numbers. So this could either be you have just a smaller set you're docking overall and you're still doing 1%, so it's a smaller fraction, or just training, a smaller fraction of the same size. So there does seem to be some room to basically reduce the size of the set. I don't know exactly how low we can reduce the set. I do know that I've experimented with dropping down like the input number of molecules to a very small number. Well, relatively small from our point of view. When I call really was like 10 million, input molecules. So that means 1% is like 100,000. And the neural net model doesn't do very well there. And I think it just overtrains at that point. So somewhere between that and a much larger set where your training set size increases, the neural net model starts to do really well in there. I don't know the exact point at which that turnover happens, like when it becomes better.
Okay.
If you actually do docking on small numbers within with Gigadock Warp in the release version right now, it actually automatically falls back to a linear model if it's a small number. And it actually requires that you have at least the training set size be at least twice the size of the number of coefficients in the neural net model, which seemed like a reasonable cutoff to use because I had to choose one, but it may be the real cutoff is a little bit variable from there, but the performance is still good.
Okay. Maybe a related question. What is the minimum batch size needed to early acquisition for training the warp model? And does this mean that it would be impossible to adapt a similar strategy for more expensive affinity metrics like MMP-BSA?
So this is really a two-part question. So I'm going to interpret what the batch size means here. So when you say batch size to me, what that means to me is if you take the training set, you usually chunk it up into pieces that you load into a GPU to do training, because the entire amount of training set won't fit in GPU memory. So that's what batch size means to me. The person asking the question might also mean just the size of the training set. So the batch size basically, in terms of what fits in GPU memory, we fit about like 2.5 million molecules, molecules, but like data points in at a time, which is a pretty decent number. These are big machines that have a lot of memory. So each epoch that we train, we basically have a bunch. I think I like that batch size because the batch size exceeds the number of coefficients in the training set. So each individual batch is unlikely to be overtrained. So one of the niceties about dealing with numbers this large is I don't really have to worry too much about the neural net model overtraining, because even though neural net models have tons of coefficients, the training set size is so big, it even exceeds that. And I think the second question is just saying is basically asking for something like MMP-BSA. Docking as a full calculation is still relatively quick compared to some other calculations. So we can dock a molecule in about a second. We're using Orion, so we have like a lot of computation that we can apply to get a large training set. But if you had a much smaller training set, would this work as well? And the answer to the question is I actually don't know for sure. I do know when I've reduced the training set size to be very, very small that the neural net model doesn't work as well. But I know there's various techniques to try to avoid the overtraining that I didn't bother to apply here at this point, because when the training set size for docking gets really, really small, you can either just do the complete docking, which is relatively inexpensive at that point, or you can switch over a linear model, which still works reasonably effectively. So I haven't really investigated, if you really try like all the modern techniques to avoid overtraining, how small you can actually get. And even without that, I don't actually know exactly what the turnover is, specifically when a linear model starts to do better than a neural net model as your training set reduces.
Yeah.
But that's about what
Next one. In a nonlinear model, there are parameters, but how many are those? How many are those in a linear model?
About 5,000
in a linear model.
Yeah, it's slightly less than
5,000.
Yeah, it's just the number of features that are that the molecules are featurized with. So they have the 4K finger, and some other things that I described earlier, but it winds up being just about 5,000 features.
Okay. I have another very general one, kind of around the docking. What scoring functions are available in OpenEye docking?
In OpenEye docking, so that's our toolkit. So that basically within our toolkits, you can use ChemGauss 4, ChemGauss 3, which is the previous version, ChemScore, PLP, or shape scoring function, or also hybrid. I should mention actually which uses ChemGauss 4 at the end, but I described this earlier, but it allows you to guide the poses with a ligand. For the flow-based versions, which I'm describing in this presentation in Orion, you have access to ChemGauss 4 scoring, which is just called Fred. You have access to hybrid, which are really the two that you want to use for the most part. Those are the most modern scoring functions that are in OE docking. There's also a fast Fred variant that I didn't describe here. It also uses ChemGauss 4 at the end, but it's a two-stage docking process. And in the initial stage, I mentioned it uses ChemGauss 3 to do the normal docking. FastRed uses PLP, which is a little bit cruder but simpler scoring function. But it still rescored the top 100 poses from each docking. Each exhaustive search docking are still rescored at the end and optimized.
The latest ChemGauss 4.
So it's a little bit faster for similar results, maybe not quite as high quality, but very close. So those are the three that are in the flows.
I think that is all the time we have today. The webinar was pretty long. Thank you, Mark, for all the work you put in. Thanks for everybody for listening and joining us here. I'm looking forward to see or hear from most of you in questions in our next webinar. Thank you very much.
Thanks a lot, everybody.